Hey everybody, it's Jeff. I just wanted to make a video about one of the many, feels like dozens of projects that I'm working on, but I just wrapped up this project called env86. And I wanted to make a sort of deep dive on this project as I wrap it up so that I can work on other things, but still let it be known and have information out there so that other people can get involved, use it, know about it, whatever. So env86 is a tool chain for embeddable emulated virtual machines in the browser and beyond based on v86, which I'll talk about a little bit later. env86 is pre one, not even 1.0, pre 0.1. Like I haven't cut a release yet because I don't have a working Linux build. There's like one thing I need to fix, but you know it works on Mac. As soon as it works on Linux, I will cut a release and it will be there. But until then, it's still fully formed. Let me give you a quick demo so you can see what it's about. So env86 primarily is used as a command line tool. And the basic workflow works like this. We will run env86 pull, and I have a repository that has an image that we can use that is surprise based on Alpine, and we'll make a copy of that image called demo. Now we can boot that VM. We're going to boot it with a network, and we're going to boot it with the save flag, which means when we quit, it will save the current state to initial state, so we can quickly iterate the state of this image. Look at that. Instantly, we're in Alpine. So in order to use networking in this case, we're going to have to run a script that's in here called networking.sh. This is going to work with a virtual network stack and get an IP. And so now we can access the internet and do things like install packages, like we'll install CMatrix. Yeah. And then we'll run it. Look at that. So cool. So we're going to go back to the command line and hit Control D. And so that's saving the state. And so now the next time we run it, we don't have to run it with any of these flags. It'll boot up immediately in that state. Okay, well that's pretty cool. Then the last part of this workflow for this tool chain here is we can use prepare to then make this something that we can put on the web. Made us a bunch of files. We can take these files and put them on any static host. Here we'll put them on a CDN. Womp womp. So first let's actually compress these files, and then we'll upload them. It seemed to do it anyway. Okay, in theory it did actually upload them. I guess we then hit deploy. And now let's check it out. Instantly in the matrix. We pulled an image with Alpine, and then we added the matrix package. We ran the matrix, then we saved the image, then we uploaded some files, and now we have a web page running this VM. We could, of course, exit out of this, and then we have a VM here in the browser. But anyway, that is the point. We were able to create a VM that we could embed on a web page. Isn't that cool? But that's not all. We can also use env86 as a Go library since it's written in Go. And this example is a little more impractical, but it's more to like make a point. We have a little Go project here, single main.go file, and then this vt.tgz, which is actually an image. And the Go program is embedding that image in it and then using env86 as a library. And we've already compiled this as Go vt. So let's see what this does. It's actually going to take a directory. So we'll give it htdocs. So it says it's starting vt. And if you've heard of vt, it's actually a JavaScript project, and it actually is built on NPM and all of this stuff. And so it's interesting that without having vt necessarily installed on this system, it's somehow starting vt. Although you'll notice it takes a little while. The reason for this is that Node.js in particular takes the longest to start in env86 or the v86 virtual machine. So less practical, but it does work. Now that it's up, let's go to this URL. It takes a little while. Hello world, served by Vite from a VM embedded in a Go executable. So that's kind of crazy. What's happening here is we're running an emulator of a Linux system running the Vite dev tool, and it's actually mounting this directory on our host into that VM so Vite can serve it, and then we're also port forwarding 3000 into the VM so that we can access it. Even though it's super slow, that's mostly Node.js's fault. Then for our last demo, this is actually a proof of concept for another project called Apptron. If you've heard of a project called Apptron that I worked on before, ignore it. This is a repurposing of the Apptron name. But again, this is still just a proof of concept. Looks like VS Code, right? It's VS Code running entirely in the browser with a full Linux development environment powered by, you guessed it, env86. There's a headless VM running on this page, and that is providing our shell here. We can see right now the file system that is being exposed to VS Code is the file system within this virtual machine. We can install packages, customize this development environment. Anyway, this is a proof of concept, and it might not seem special, but other than this sort of like network relay, this network gateway giving it internet access, this VM, VS Code is running without anything running in the cloud other than a CDN. This is all happening with static files, not that different from the static files that we deployed to Cloudflare. Apptron is what I'm going to be working on next now that env86 is sort of in a more or less done enough state for me. So env86 makes and runs x86-based system environments that you can embed on web pages and, as you saw experimentally, in Go programs. As a little bit of background, env86 is based on this amazing project called v86. So v86 is an x86 to WASM JIT. And compared to pretty much any other emulator that runs in the browser, I believe this is the fastest one. It's not super well known. I sort of discovered it through my friends while they were working on playable quotes. So let's take a look at some demos here. Windows 98. Instantly, we're in Windows 98 in your browser. This even works on mobile. We also have Plan 9, or in this case, 9front, because I love Plan 9, and it's kind of a pain to use as an actual operating system, but here we can play with it in the browser, which is really cool. We also have Haiku, which is an open source BOS, which was another cool operating system from the 90s. It supports a bunch of old retro and open source operating systems. But it also, of course, runs Linux. So here it's running Arch without any desktop or anything. So caveats to v86. As you can see from this repository, it is very much like a hacker project. There's not like a ton of documentation, so you end up having to read the source. People are pretty helpful on the forums and stuff like that. But the main thing is that it is emulating a full computer in software. So it will run slower than native software, but it'll also run slower than programs that are compiled to WASM because it itself is running in WASM and then running the software. So we're trading performance for compatibility. And so that's a big thing. The point is not performance. We will always have a performance hit. But at least v86, as far as I know, is the fastest open source WebAssembly x86 emulator. The other caveat, the big one, is that it is a 32-bit architecture. It will only run x86 32 or i386. It will not run 64-bit programs, but we will talk about that later. If you want internet access, you have to run a WebSocket relay service that only runs on Linux. But really the big caveat is that it's just kind of a pain to make images for this thing. Like if you want to use this for a particular purpose, you're probably going to make a custom image. And so making custom images for v86 or any emulator or VM is not very fun. This is why tools like Packer exist. And you can also use tools like QEMU, which itself is an emulator, much more powerful and complicated. You can also use Docker to build images with some caveats and some extra scripts, but then you have to make sure that it actually works with the generic hardware that it provides, has the right drivers, has 9p module in the Linux kernel so that it can do its 9p root file system thing, have auto login, all that kind of stuff. And then you can customize the environment to have, the programs and libraries or whatever that you want in it that you're actually going to use. But of course, to install those, you'll need networking. So you're going to have to deal with setting up the relay and dealing with the network complications. And then you need to build initial state so that you can get these images that basically, since it's really made for booting in the browser, that it happens immediately. And you want to automate all of this. Plus, it only runs in the browser, which, if it wasn't a lot of work to author images, now you have to test those images, you have to set up a web page and configure this. And then if it doesn't work, you don't know if it's your configurations getting v86 to start or if it's your image, right? So it felt like there were a lot of challenges working with v86, even though it is an amazing project. So env86 was conceived to originally make building v86 images easier, but then also run v86 images outside the browser, script usage and authoring of v86 images on the shell, provide a more powerful cross-platform networking stack, overall make an experience that's closer to Docker, including port forwarding and directory mounting, prepare files for deploying on the web, and conventions to make a more standard image format, which makes sharing and using pre-made images easier. The goal is to make v86 more accessible as a primitive for building software systems that need to embed full system environments, hence env86. Why? Well, if you'll allow me to philosophize here, let me set up an appropriate backdrop. Virtualization, emulation, containers, and now WebAssembly or WASM are very cool, powerful technologies that open up new possibilities in our software by making software itself more programmable and more universal. They also all effectively provide some form of isolation or some level of sandboxing that has, for example, powered the multi-tenancy of cloud computing. And now with WebAssembly being the most lightweight, we can sandbox and embed within pretty much any program executable. For example, lightweight WebAssembly sandboxing opens up running untrusted user code directly in our applications, which is basically an alternative to like webhooks or really any other kinds of hooks. But also, we can use it for running code from, say, LLMs and AI, and give AI and AI agents a secure sandbox to do interesting things in. But compared to containers, WASM adoption is taking a while. And so not everything can be compiled to and run in WASM yet. So this is why emulation is important, because it can sort of fill the gap. If you can't run something as WASM directly yet, you can probably run it in a WASM emulator, like v86. Let's talk really quickly about the i386 32-bit architecture thing. Let's do it with a different backdrop. Here we go. So i386 and 32-bit. First of all, this isn't a forever constraint. There is an open issue on the v86 repository. Despite being described as very difficult to make v86 support 64-bit architecture. But in the meantime, and maybe you've already been thinking, wait, 32-bit, isn't that like deprecated? I mean, how much Linux software even distributes 32-bit binaries. Not a lot. But you can usually still build a lot of software for 32-bit architecture if you build it from source yourself. That said, good old Alpine Linux, which I helped popularize for Docker because it was small and has an amazing package repository, turns out to have i386 builds for nearly every package in its repository. So unless anybody knows of another, which definitely let me know, I think Alpine is the smallest Linux distro with the largest collection of 32-bit packages. So this is why, despite the libc thing, I still use Alpine as my go-to distro for Docker, but now especially for v86. Anyway, I'm not saying this 32-bit constraint won't present a challenge in some cases, just that it might not be as big a constraint as you might think. It'll certainly present challenges for NPM packages using native extensions. I've already run into that, but I've also started to notice a trend of Node.js projects that have native extensions also having a WebAssembly alternative that you can use, which will run in env86. So that's v86 and what env86 is about and why I spent the last month or so putting it together. Even though I haven't cut a release yet, it's pretty much fully formed and usable, at least on Mac and soon Linux. Someday I'm sure on Windows too. And now that it solves my main use cases, I can move back up the axe shaving stack and work on Aptron, which you saw earlier. Just in case env86 is interesting to anybody out there, I wanted to now talk about how it works in the off chance that somebody wants to use or contribute to the project. So let's take a look at the source, starting with the makefile. So basically how you would build the project. It's not just a simple Go build. There are static assets that we generate, and there's a sort of secondary binary that we also generate. So I just want to review this really quick. Here's our Go build. If you do a make build, that'll build the binary. This make install is just going to copy it into user local bin, which is more for me than anybody else. Feel free not to use that. And again, the release stuff is also for me. But then look at these assets. So you can say make assets, and it's got kind of three things here. One is the guest service binary. So it's always going to build that for Linux 386, and then it just puts it into assets. And then we have kernel and v86. And these are both run in Docker containers, and we'll look at the scripts for those. I'm sort of wrapping the scripts to produce these in Docker containers because they have certain dependencies themselves, and it's just easier to run them in a consistent environment. So if you are building this, you want to make sure that you have Docker installed until there's a binary that you can download, and then that won't be an issue at all. So kernel is basically Linux kernel and a init RAM that we're going to embed in env86 to use by default. And then, of course, v86 is the v86 project and some assets. So you should be able to make all the first time, and then you can do make build. Anyway, simple make file. Let's look at the scripts for those Docker files. Again, just to kind of give you an idea of what's going on here. Here's v86. So all of these are going to be in Alpine. We're just cloning v86, and we build it. It's a Rust project. And then the assets that we grab out of it is the v86 WASM, the libv86 JavaScript library that's used to wrap and set up the v86 WASM, and then two BIOS binaries. When you're setting up v86 and you're booting from scratch, you need to specify a BIOS and a VGA BIOS, and so these come with v86, and so we grab these as well and put them in assets. Kernel, I don't know if this is the best. This is just a subset of if I were to build, a Linux kernel with the kernel and init RAM. This is the script. This is the Docker file that I'd use. So the main thing is, I think, a certain version of the kernel. Well, it's LTS, and then also that we make sure that there's a 9p module. and then the output are those two files. There's just to look at scripts now. Dockerfile example is basically a usable with env86 create from Docker. So if you said from Docker and then point to this Docker file, it will build a usable Alpine v86 image. And you can see here that it is the i386 version of Alpine. I don't know if this includes stuff that is, I don't know how much of this we could get rid of, but I know that we do need some of it. Obviously, like the networking stuff is helpful to have in there. The TTY stuff you want to have set up. Anyway, so this is not necessarily the most minimal thing, but this works. So you can use this. Dockerfile build actually kind of contains these other ones because it's actually going to build all of env86 in a container. And this is specifically for building an AMD64 Linux build to use on GitHub Actions. And so we kind of have minimal versions of those other ones to produce the assets, and then we create a container to build the guest and env86 itself, but we also have Chromium in here. So this is made to be used with the CDP flag and headless Chrome. So this works on GitHub Actions and is available on Docker Hub as program/env86. That's pretty much all that's in scripts. So let's look at assets. We're sort of walking around the main project code. So you can see in assets, a bunch of things are get ignored. Those are all the files that we generate. I mentioned most of these here. There is the JavaScript env86 library. This is what you actually use. We sort of wrap libv86, which is already minified here. The API that we use when we sort of deploy env86 is this one, which has this boot function. This might change a little bit, but anyway, it's mostly just doing config and setting things up, assuming that you might have the control endpoint and TTY stuff set up in the guest service. But it's pretty much wrapping, setting up v86. And also exposing a lot of the methods on the v86 JavaScript API that we want to use from Go. So we expose that over duplex RPC, which means we also depend on duplex, and that's just sort of vendored here, like I often do. And then there's index.html and console, and they're pretty much identical. Console is what's used when you actually boot, and so it creates a web view window of a console. It's using this. And then index.html is what it gives you when you prepare an image. This is sort of the default index.html when you prepare for being published. So I don't know how much they're always going to be in sync. Maybe we could just make them one file, but right now they're separate. And because we're embedding all of these into env86, we do this by having a Go file in here that just embeds them all in here. This little trick is something that I usually do when I embed files like this because it makes, instead of using assets here, we export dir, which is a file system that when you run it, it will actually check to see if we're in the repository so that it will, if the embedded file is on your host, it will use that instead of what's actually embedded in the binary. And this allows you to make changes to files and not have to worry about like recompiling. It also handles like file changes and stuff too. Anyway, the other thing in here that's interesting is bundled JavaScript. So we minify and bundle the env86, JS, and duplex together using esbuild, which is Go, so we can use it as a library here. And then libv86, since it's already minified, already sort of bundled, and wouldn't properly bundle if we tried to anyway, we actually just prepend it to the output bytes here that usually is going to show up as env86.min.js. So that is usually the bundled version. So these are all the static assets that are going to be bundled in the env86 binary. Some of them define some of the API. Some of them are just things that, obviously like v86. So one of them is the guest service, guest86. And so let's look at that really quick because it's much simpler. So we can kind of ease into this. So guest86 is a very simple Go program. It listens on whatever specified or the default serial port and just serves duplex RPC based on this API struct. So all the methods on this struct are going to be exported as RPC callable things. We've got version in here. This is sort of temporary. It's basically that networking.sh script, but as an RPC call, so we can do that. It's kind of specific to Alpine, so this is sort of temporary. Otherwise, each of the sort of like different parts of the API are in different files. We've got fs, which is a very minimal sort of like way to expose the internal file system of the virtual machine. We've got a stat, we've got a read file, we've got a read dir, a write file, and a make dir. And so this, for example, is used by the VS Code extension this is what exposes the file system to the VS Code extension in Apptron, for example. Then another simple thing here is we have a dial method. So this lets you dial a TCP socket from within the VM, and it takes basically an address. And you can see this by the signature. That usually means that we're going to be doing a stream instead of just a normal kind of unary function call. We then dial that address and we get a connection, and then we join it with our with the channel that was made for this call. So pretty simple. It lets us kind of tunnel connections in here or dial things from the outside. Let's see, we've got TTY, which is pretty much the same thing, right? Except instead of dialing a TCP address, we're running a shell command subprocess. We do pretty much the exact same thing here. We run as a PTY. This actually might just get removed because we have a more generic version of this, which is the exec run. And let's see, yep. So this is made to more or less feel on the client side a lot like OS exec, so running a subprocess in Go, but we implement it with basically one RPC method. We take in run input that looks a lot like the command structure from OS exec. We run the command. We have the option. What's different is you can also pass whether you want to run it in as a PTY. So we'll run it a little bit differently if that's the case. We run it, we wait for it to run, we get the status, and we return the status code. And if we run it as a PTY, we start it as a PTY, we immediately return the PID, since I think we would have some other things here, because if you want to signal it or terminate it by PID, these aren't implemented yet. So you would get that immediately on the other end. And then otherwise very similar, we're just joining with the channel. It looks like, though, because in the case of running it without a PTY, you want to have standard out and standard error separate. So the way this works in both cases is instead of just treating it like a byte stream, the channel, once we sort of stream it, we actually stream a bunch of values. These run output values, which lets us either define standard out bytes, standard error bytes, or a status. And so this lets us kind of shortcut to having like multiple byte channels and then also sending the status when we're done. Anyway, so this could replace TTY, but it lets us run subprocesses in the VM. Lastly, the most kind of complicated one, in a way, is the mount API, and there's supposed to be two of them. One of them is supposed to, which is obviously not implemented, is going to be implemented using Fuse. So it would create a Fuse file system. And when you create a Fuse file system, you implement certain methods that would normally be called by the operating system when you do stuff like an open and a read. And the idea here is that we would delegate those methods over RPC. So we'd call back to the caller so that the caller of the guest API can provide a Fuse file system. And this is specifically for the case in the browser where we want to expose the in-browser file system API. So you open up a local file directory and we want to expose that to the VM. We would have like the file handle and directory handle JavaScript objects, and we would wrap those with like a duplex API that this would then be able to call for Fuse stuff. So that's yet to be done. But what we do have is mount 9p. And this is a little complicated, but the idea is you would call this on the client side, you'd start a 9p server, and then you'd connect to it, and then you'd hold that connection, and then you'd dial or make this call, mount 9p. You'd say what the mount path is inside the VM you want to mount at. And then in here, we're going to do a listen, because we're ultimately using the normal mount command to mount a normal 9p file system over TCP. So in the VM, we listen on an unused port, and then we call mount, so there's going to be one connection to it, so we do one accept, and once we get that connection, we then join that with the channel, which is then going to be joined on the other end with the connection that we made to 9p. So it's kind of like a weird plumbing thing where we kind of connect up these two things. We're doing a listen on both ends. It's a little weird, but it works. So then this talks to this port, and it ends up talking to the 9p server on the outside. So that's the guest service. That's pretty much all there is. If you wanted to extend the guest service with custom stuff, you could do that pretty easily. But this is sort of like the standard guest service. All right, now let's talk about env86. And like I mentioned, env86 is sort of both a command line CLI tool, but this is mostly just wrapping a Go package that you can use in your own Go programs. And so I'm mostly going to talk about the CLI, so you can see how it works, how each of the commands work. And then I'm only going to briefly talk about the library, because most of it's plumbing. And so it's kind of boring. So let's go through this. env86, finally, the real code of the system. You can see that we have a kind of a command framework here that it's more or less loosely based on Cobra. And this is kind of important. The library that we use, that I wrote for doing desktop things like creating windows and web view windows and menus and a lot of stuff that this doesn't use. We only use it for web view windows. Anytime you do any of that stuff, you need to reserve the main thread for the operating systems like GUI drawing stuff. So we always have to, if we're going to use that stuff, we have to run through desktop start, which then runs the rest of your program in another Go routine, and then the original Go routine is sort of locked, and we reserve that so that when you start the event loop or the operating system APIs, they can start it in the main thread. Then there's sort of just like a couple of helpers in here. We have this idea of like a global. Most of the time your images might be a relative path because it's like pointing to a directory or a tarball. And so an image is just, a file in the file system. But then we have this idea of like a global system repository, or I don't know what to call it. But basically we assume that you might want to have, basically we'll put everything in a .env86 in your home directory, and you can override this by changing this environment variable. But this is where we're going to put all of the images that you would pull from a repository, and you can also, basically anything that's not a relative path will be put there. And then we have this function which really needs some tests, but basically the idea is, when you're doing a pull or referencing something like a repository, an image that you're going to download or something like that, which includes a version or a tag similar to Docker tags. And this gets complicated, like if you specify it or if you don't specify it, and yada, yada, yada. Basically, this function will convert this into the actual path that it will use to store or read the image. So all this is doing is like giving us a path and telling us whether or not it exists. And it's not that complicated, but it's just kind of tricky to make. So let's go into the actual subcommands. We'll start with pull because that might be, in terms of workflow, the first command that you use. It's maybe one of the most complicated things here, but mostly because it's just a bunch of steps working with GitHub URLs. So you can see we can say env86 pull and a repo, not a URL with a protocol. Right now it can only be GitHub, and then optionally you can specify a tag. If you don't, it will default to latest, which will be whatever the latest release is. So this is also defining the conventions for how you would set up a repo to publish on GitHub that can be pulled by this. So pretty straightforward. What's cool is we don't actually use the GitHub API at all. We can do this all with the normal GitHub URLs. The only interesting kind of thing here is that you can optionally suffix your repositories with -env86. And so you don't have to specify -env86 when you give repository user URLs here, but that way you can sort of differentiate them, for yourself. That, this is a repository is an env86 image, not like a fork of Alpine or something like that. And if you don't specify a tag, then it will assume latest, which it will actually just go to the URL latest, which will redirect to the latest release. And then it's always going to use release assets. And the release assets basically always need to be in the format of the base name of the repository, not including env86, dash the tag as a tarball. And so with that, you can publish. And I guess I can show you just as a little diversion, we can look at an example of this. So this is an example repository, the only one that exists, what I used to develop Pol with. But you can see I call Alpine env86. This is basically defining a Docker file that we're going to use to create the env86 image. Looks familiar, right? And so really the big thing in here is the GitHub action. And so this is what you would copy if you wanted to do the same thing. There are a couple of just tricks in here. GitHub doesn't run actions with a TTY, so this kind of gets around that because we need that. We're doing this build using the program env86 image on Docker Hub, which I mentioned we made. And so we can just, these steps happen inside that container. And in that container, we need to use Docker, so we set up Docker and Docker. So we do a checkout, we create the image with the normal workflow, doing a create from Docker file. Then we do a boot using CDP, since this image has headless Chrome, that will exit on prompt. So this will set up an initial state. And then we tar-gz that into a file, which we then release. So this is what Pol is expecting. Okay. And that's Pol. You can see here, not quite done yet, because once we figure out what version the latest is, then we're going to use that. You saw it was like 3.18, and we would actually store that as a particular directory and then symlink latest to that in the env86 global image directory. Okay, create. This is another bigger one. So these are the commands that aren't actually using the library. They're really just implementing it all in the command here. So create here, you can say create. You're going to give it an image. This does not yet support global images, creating them directly into your .env86 directory yet. And you can see there are a couple of flags. You kind of always need to specify either from dir, so this is a file system, a Linux file system root that we're going to use, or we can say from Docker, which can either be a Docker image or a Docker file, and this of course assumes that you have Docker installed. And then there's a with guest option, which will basically take our embedded env86 and put it into bin/bin in the file system. You can see it's pretty straightforward the way we check to see if you specified a dir. Okay, does the directory exist? If you specified from Docker, we're going to check to see if it's a file. If it's a file that exists, we assume it's a Docker file, so we do a Docker build. And then once it's a Docker build, it's basically the same thing as an image. So then we would do the same thing whether you're doing a Docker file or an image, where we run Docker create. Notice the platform Linux 386. We do an export, which will give us the entire file system as a tar. Then we delete it. Then we untar it. We make sure it has reasonable permissions. We remove the tar file and this Docker end file that always comes out of Docker export. And then we set that to the directory as if we were doing a from dir. So all this is in a temporary directory. So then we just do a final check to see, is this in the do we have a directory set? Here's where we do the check. Hey, now that we have a directory, did you want to put in the guest binary? Then we just copy it in from assets. And then here is where we do some of the kind of custom stuff that's specific to v86. we generate the sort of flat file system or on-demand file system that requires creating a JSON file index of all the files, and then also basically taking every file in there and then putting them in a sort of like content addressable directory where it's all the same files that would be in the file system, but in a single directory, all named with a SHA of their contents. So that's a v86 thing. These were originally Python scripts, but my friend Michael ported those to Go, and so you don't need those Python scripts here. It's just going to do that automatically. It sets up the default config that'll be stored with the image, which is pretty much just the boot command, and this is pretty common for Linux. If this is not what you want, you can just change it afterwards. If there was a guest, we note that in the config. We check to see if your file system has a bootable kernel and an initRD, because if you do, then we will set the option to tell v86 to use it from the file system. Otherwise, the option is you can specify your own in the config when you run a VM, or if you don't specify anything, it will use the ones that we embedded. So that's what those ones are for. And then we write the image.json, and all this is now in a directory. And that directory is now, we'll call it an env86 image. Possibly there could be an option here to like make it a tarball instead of a directory, or maybe if the image path that you specify, if it ends with TGZ, maybe it'll tarball it up. It doesn't do that yet. You can always do that manually. Okay, create now boot. This is the meat of it, which interestingly, this has kind of the least stuff in it because we're mostly delegating to our library. But you can see this is where all our flags are, all these lovely flags. And so what we do is we get the image. Here we do support the global path, so this is what it would look like in pretty much any command that would take an image. Then we use the env86 load image function, which will give us sort of an unpacked image that we have some methods on that we can use, including config. So this is going to pull the default config out, which is more or less the image.json. And then we take our flag values and we set them on the config. Then we create an env86 VM based on the image and our new config. And we start it in this sort of asynchronous mode. And then we call VM wait. So it's just going to block until the VM is done. So the magic is in start. I'll show you, that's like the one thing I'll show you in the library when we get to it. But otherwise, while that's running, if you specified console URL, we're going to output that there for debugging. If you didn't specify a TTY, if you didn't enable TTY, we still need to listen on standard in to see if you hit Control D. So we do that here. If you enable the network is set up with the VM that it will use, but we do a couple of things outside here for now. This is kind of like a temporary hack experiment. You can set up a VM to preserve its MAC address across boots, which means you don't have to reset the NIC every time and get a new IP. However, assuming the network still exists, you just want to make sure that the network, that virtual network switch has you in the route table. So we just send a ping. Again, this is assuming that we're booting into a terminal state. So this is not ideal. And if you specified a port forward, then we run our port forwarder function here, which you can see it's very straightforward. Listens on a port, that you specified. Our VM, we assume right now, is always .2, and then we dial it using the virtual network, and then we bridge those connections. So that's boot, the most complicated thing. We got it out of the way. Then there's run, and so run is one of the newest commands, and the idea was to make a command that was more like Docker run, which assumes that you don't care about booting, you just want to run a command, right? You don't necessarily want to deal with, I'm booting a VM, what state is it in, am I in a terminal, can I just send some text that will let me start a program? So this gives you that structured API. This ultimately uses the command run API of the guest service. So this requires the guest service, and then it works a lot like Docker run. You specify the image, you specify a command, and then any arguments. So this also assumes that the image has initial state, and that initial state is going to take us into a state where the guest service is running. So it's very similar to boot. except once we've started up, we're going to check for the guest. This is just sort of there for now, which actually makes it kind of slow. I haven't figured out like a consistent way, or what is the convention with networking, if we always want to do a preserve MAC, how we always want to reset this. So it's a little inconsistent. This might change. The problem is that this is slow. So this is currently kind of a slow command to run right now. If we specified a directory to mount, we set that up here. And again, all we have to do is call guest mount. And then we do the same thing with the networking if we do a port forwarding. And then again, use the guest API. It looks a lot like OS exec. We say command, give it the arguments. We can set up standard in, standard out, error. Since we assume we're attaching to the terminal, we do make raw on standard in, which we restore. Then we do command run, and we wait for the command to finish. Then we tell the VM to stop, and then we exit this with the status of the program's exit status. Pretty simple. Prepare. So now you've got your VM image ready to publish on the web. And so you can't just take your image directory and put it on the web. You have to prepare it. And so this creates a directory based on an image that we can actually just put on a static host. So we load up the image. And then the image type actually has a prepare method that will return part of what we want here. It's going to return the image part of the directory. So we use file systems as an abstraction here. Whenever we work with like a directory, we will often treat that as a file system. And so this returns a file system called prepared image that is basically an in-memory file system. We can look at that real quick since we don't need to look at it later. You can see that there is a base file system that when you set up the image that we have that we're going to use, but then we do stuff like, is there initial state? Because if there is an initial state, then we also need to include, these extra files necessary to boot. So that gives us a base image directory. Our destination, wherever we're going to write these, we create a little OSFS destination file system. In there we create an image directory, and then we copy that into image. Anyway, long story short, the image goes into /image. And I guess prepare will also chunk up your initial state. But that's not all we want. If we need to run this on the web, we need the v86 WASM, we need our env86 JavaScript, which we bundle here, and we just write these in, and then we write in our index.html. So that's prepare. And then serve is kind of, it's different from boot. It doesn't have all the same options. It's more or less a preview of prepare. It's like you ran prepare and then ran an HTTP server in that directory. That's more or less what serve does. It's going to do the same thing and then run an HTTP service, which you can then hit with a browser to see what it would look like if you deployed this. I don't know if that should be called preview or what, but I assume that you're going to customize the index and stuff like that. So preview is not necessarily the right way to describe it. The only two things that are left is the network command. So normally when you boot or run, you create a VM. With the library, we create a virtual network if you said that you want it to have networking. If you deploy this, you now have to connect over WebSocket to a relay or something that provides this virtual network. And that's what this command does. So there's not a lot of options. So far, we're just hard-coding the same values all the time. At some point, maybe these can be configurable, but for now, these are all just kind of hard-coded. But yeah, network just sets up a virtual network the same way we do if we were to boot a VM. And then we have a handler that will then create a WebSocket service. And so we just serve that over HTTP. That's all this does. Then there's a hidden command. It's sort of a debug command, but all those assets that we have in here, what if we have the env86 binary and we want to get one of these assets out for debugging, or we want to get, env86.min out, or v8, whatever. You can actually say assets in the file name, and it will output to standard out that file. So hidden sort of debug command. So that's the env86 commands. And most of the heavy lifting here is done in the library, which I'm going to leave as an exercise for the viewer to look at. It's mostly boring plumbing and config. these packages, tarfs, namespacefs, fsutil, these are temporary in that eventually they're going to live in toolkit.go. But whenever I make something or do something new, it's going to live in the repository that I'm using it before I put it into the shared place. But I will share the main conceit. The way we're running v86 outside of the browser is we're running it in the browser. So as you may have noticed, I said that we run desktop APIs to create a web view window. And if we look at VM start, that's pretty much what we do. We create a new web view window. We serve some HTTP. It also has a WebSocket API that basically bridges the browser environment with our Go code, so we can call functions in either directions and communicate and signal between them. But otherwise, we're always running it in a web view. Even when you turn the console, we say no console, or you want to run this in headless mode, we just hide the window. So it's still there. It's a headless web view that we run this in. And then you can see that if you're running in Chrome DP mode, we use Chrome DP instead, headless Chrome. So that's really it. I mean, we could go through kind of the path. We saw load image is kind of usually where we start. That gives us an image, which we could also load from a reader. And then typically we get a config out of that as our default config. We customize it, and then we'll call VM new, which is basically going to do a lot of config setup. Here's something that's hard-coded that shouldn't be, the default memory size and VGA memory size. I don't know what a good default is, and obviously this should be customizable, but I've kind of left that out. So submit a PR, please, to fix that. We customize the config based on, it's all just boring config stuff. Set up the network, and then you call start, which you can see what it does. The HTTP service basically looks like this. Here's a shape of it. It's more or less serving basically everything under assets at root. And then we pre-bundle our env86 library and serve that as well. And then there's these 3 endpoints that are used. /net is how v86 connects over WebSocket to get the network. So this is what's channeling all the Ethernet packets from the virtual NIC to our virtual network stack. Guest is basically going to connect if we're running a guest in the VM, we'll set up this WebSocket connection, and then on the other end, this is how we can call guest methods. It's basically then tunneled into the VM, and then everything else over the API is done over this control endpoint. And so you can see some of the stuff on this side that's exposed to the web side, and then you saw in our assets what's exposed on the web side to the Go side that we can call. That's pretty much it. I mentioned the file system abstraction that we use quite a bit. I mentioned these temporary packages. So yeah, that's pretty much it. What next? Really briefly, we can talk about. Obviously, the most important thing is to get this running on Linux. The reason why there isn't a release is I don't have a Linux build that works because the library that I'm using for making WebView windows, I think has some bugs for Linux, and so I need to implement those. So it's an upstream thing of my own library that's preventing me from creating a working Linux build here. Once I fix those, then we can kind of release. If anybody wants to help with that, I'd love it. I don't really like writing Linux-specific stuff. I don't even have a Linux set up here. I'd have to use env86 or something to test it. Anyway, there's a lot of rough edges. There's probably bugs, things that should communicate more. Feel free to submit PRs for fixing any of those things. I mentioned the fuse mount API. You saw a couple of things that are sort of to-do things to implement. One of the things that I do want to implement at some point, but it just isn't necessary yet, is now that we have the guest services and run, we can kind of make our own Docker build and our own Docker file. Maybe call it an env file, where we can say from, and then specify an image, repository, like GitHub/program/Alpine. And then you can specify runs, and you can imagine they would just take the base image and then do those runs in order, copy files in using mount, command. It could be more or less Dockerfile compatible, similar syntax. It doesn't need to be the same thing. I'm just saying we could make something like that, and maybe we should. I don't know. Maybe it'd be nice. So then you can say env86 build instead of using env86 create from Docker, because then we don't need Docker. And then based on demand, I can imagine better support for non-Linux operating systems and more configurable networking. I don't know. We'll see. So that's it. That's everything you need to know if you want to get into this project. I would really appreciate it if you do decide to use it, but especially if you contribute in some way, since I will be working on other things. So that's it. That's env86. Thanks for sitting through that. See you later.